We are very happy to have David Balabio here today. He's going to give a webinar on how to deal with identification of spectra from LC-MS, something that many people are struggling with. So we look very much forward to that. Please keep yourself muted. If you have clarifying questions during the talk, you can send them in the chat and I will convey them. But more sort of, let's say, more general questions, we take them in the end. And I would also just like to stress that we are recording this and we will put it on YouTube after today. So we expect that you agree to that. So David, please.
Okay, Rasmus. So as usual, first of all, thank you for the invitation, for the opportunity. I mean, this is a topic I have been working in the last 2 years with the research group I'm working with. So I'm based in Milan. I'm part of the Milano Chemometrics and QSAR research group. And actually, this topic is a good combination of the skills of the people who is in the group, which is part QSAR and part is, let's say, experimental analytical chemistry, okay? And besides this, I mean, I found this topic very challenging in a chemometric point of view, and this is why I try to start to work on this in this framework, okay? So what is about is how to use chemometrics and let's say molecular descriptors, which are molecular fingerprints in this case, to enhance the annotation of compounds through LC-MS signals data, okay? So just to give you a short introduction, when you measure a mass spectra, okay, for a sample, okay, then you are interested to, through, of course, liquid chromatography coupled with mass spectrometry, then you are interested to match the mass spectra with a spectral library in order to identify the compound. Okay, so usually we have a spectral library which are linked to the instrument we use, and then the matching enable the identification of the compound. Okay, there are some issues because these spectral libraries are, let's say, relatively limited, and they also depend on the type of instrument, okay? And so I found this data in a paper published a couple of years ago. So less than 10% of metabolites have experimental reference mass spectra, okay? So which is the issue? Is that especially when you deal with omics, untargeted omics application, okay, you have some cases. So, for example, you can measure your mass spectra. You want to identify the compound associated with this spectra, but the library does not contain the target spectrum, okay? Or the library contains the spectrum of the target compound, but this was measured in different experimental condition or with a different instrument, and so the matching does not work, okay? This can happen, and so what happens? In the, let's say, latest 10 years, more or less, different approaches, computational approaches have been proposed to enhance the identification of compounds based on mass spectra, okay? Which are these cases? Here you have some references, okay? So this is just a very short, let's say, identification. But one option is to use rule-based fragmentation. So it means that you have fragmentation rules, and this gives you a set of candidate molecular structure. And then you try to match these candidates with the mass spectra that has been measured. Okay. Then you have combinatorial fragmentation, where you have a lot of possible fragments which are systematically calculated, breaking bonds. Okay. Or you have competitive fragmentation, which tries to predict the peaks with a probabilistic generative approach, okay, for the fragmentation process. Behind all these approaches, then there is another one, which implies the use of, let's say, machine learning and chemometrics in this case, okay, because here we deal with chemical data. How is the idea? Okay, when you have a compound, okay, for every compound, of course, if you know the molecular structure of the compound, then you can easily calculate the so-called molecular descriptors. Molecular descriptors are numbers which describe and code the molecular structure of the compound. And this can be easily calculated, and a specific type of molecular descriptor are the binary fingerprints. These are give you, let's say, an holistic overview of the structure of the chemical, okay? And you can see for each chemical, you get basically a binary vector which describes the presence of structural patterns. So you have activated bits and not activated bits, and this vector is a binary vector and gives you the description of the molecular structure of the compound. The idea, okay, is to be somehow, by means of chemometrics, to find a model which is able to calculate a relationship between the mass spectra and the fingerprints. Okay, if we are able to do this, so the mass spectra are, let's say, the dependent variable, and the fingerprints are the independent variable, the y, okay, responses. Okay, if we are able to get this model, and if this model is enough accurate, then, which is the advantage, we can use the fingerprints, okay, to search for our compound in online libraries and online databases, okay, based on fingerprints, which are wider and independent from instruments, okay? So, for example, in PubChem, you have millions of structures which are associated to the fingerprints, sorry, millions of compounds which are associated to the fingerprints. So then you can match actually the outcome, the fingerprints predicted from the mass spectra to these huge databases in order to enhance the annotation, so the matching and the search for the compound which is associated to the mass spectra, okay? So just to give you an idea, 4 years ago now, I mean, we are in 2023 now. So 4 years ago, it was published this review, okay, which is, I mean, a nice, I guess, point to start, because it's about the all the approaches, okay, based on machine learning, okay, to enhance the metabolite identification, okay, starting from MS data. So this is a suggestion I give you, okay, because even for me it was a nice point to start with. And these are this is another study I use it as a benchmark for our modeling approach. Here, authors used around 180,000 spectra to train a neural network to predict molecular fingerprints. Okay, so the approach I explained it before. Another nice reference paper is this one, if you want. I mean, I presented this work last August in a conference, and when I was preparing the slides for the conference, I found out this paper. Because it was published a few weeks before. It's from 2022, if you can, as you can see, and it's again about the application here of kernel, supervector machine, and deep neural networks on a huge database of 156,000 compounds, okay? Again, to predict, okay, fingerprints to enhance the identification of molecules starting from mass spectral data, okay? And if you want here, the authors also provide the, I guess, somehow the models they use it in this Sirius software, which is available online, okay? So it could be a nice benchmark. This is the what we did so far. So let's say the preliminary results we obtained, which is the what I'm going to show you in this webinar. And if you want, I mean, all the data I will describe and which have been used to calibrate our model are available on our website. So if you are interested to play a bit with in this framework, you can download the data we have used for our models. Okay, here this is the link, and then you can get the PDF file of the slides if you want from the chat of the webinar, or you can email me, and I can send you all the details. So to reset a bit, so which is the aim? The aim is to get a model, okay? In this case, and then I will explain why we use neural networks, but in this case, neural networks to get a model which is able to predict molecular fingerprints, so binary molecular fingerprints starting from LC-MS, so MS spectra, okay, measured in tandem with liquid chromatography to enhance the annotation, the identification of compounds, okay? And as I said, there are a lot of issues doing this, and this is why I say that this is very challenging in a chemometric point of view, because you have the big data issue, okay? Because we are dealing with a lot of data. With neural networks, which were, I mean, I'm let's say a little bit old. I consider myself old now. And so I wasn't used to play a lot with neural networks, but I mean, using these approaches implies a lot of tuning. And then you have a lot of opportunities to evaluate the similarity between the fingerprint and the fingerprint databases you have online. So how to do that? Another issue is the sparseness of the data you have, because both the fingerprints, which are binary data, and the mass spectra are very, very sparse, okay? So a lot of things to, let's say, play with, okay? So how we organized our modeling part. So we started from the data. So we needed a lot of mass spectra to train our data, okay? We used only open repository, and basically we downloaded the spectra from the Mass Bank of North America database, around 140,000 spectra, okay, mass spectra. Of course, then we did some data curation, okay, because we wanted to avoid let's say, noisy information. So each spectra was associated with information on the type of instrument and the experimental condition which have been used for the measurement. So we deleted all the records without this information. We deleted all the spectra with inconsistency between the molecular weight and the precursor ions. We only retained the spectra which were measured in the positive ionization mode, and we retained only spectra which were measured with a range of collision energy between 5 and 70. And then we did also other curation step. We retained just spectra with the most common precursor ions. And if we found peaks at the hem zeta higher than the precursor ions, then we removed those peaks. Okay, so finally, we retained a data set including 40,000 spectra, more or less. Okay, These spectra were associated with 5,500 chemicals. Okay, this means that for the same chemical, we can have different mass spectra, which were measured in different experimental conditions. Okay, here you have two options. You can merge some people merge the information from all the spectra to get a unique super spectrum, let's say. So they try to combine the information. We used an opposite approach, and we retained all the separate spectra. Okay. After that, we have to, let's say again, play a bit with the data and do some data curing, and we had to standardize the length of the mass spectra, okay, for all the entries of the database, or the data set, okay. So we decided to use a range for the mass spectra between 45 and 7, more or less 700, because this was the most comprehensive range where we had peaks in the whole data set, okay? And then again, we decided to get a resolution for the data set at 1 decimal point, okay? Because this was our first preliminary tentative for modeling this data. And in this way, we could reduce the sparseness of the data, and we could get a, let's say, more reasonable data size, okay? Because in this way, you get for each spectra, you have a vector of length equal to around 6,500 values, okay? So after that, okay, we were okay with the part related to the mass spectra, but we needed also the binary fingerprints, okay? So if you don't know what is a binary fingerprint, it's just a binary vector, okay, with a fixed length, and it's a, let's say, a comprehensive representation of the molecular structure, okay? These bits encode the presence or absence of structural features in a chemical, okay? So for each chemical, you can easily get with the softwares, okay? So this is an in-silico calculation, okay? You input the structure as a smile in a software, and you get this vector, okay? There are a lot of types of fingerprints, and we decided to use these, which are called McKee's binary fingerprints, which have a fixed length of 166 bits, okay? Why? Again, because in a computational point of view, these were more easy to reduce than to simplify the modeling part and to reduce sparseness, okay, in the binary fingerprint data, okay? So what happens is that then, okay, in the fingerprints, you have some bits which are activated on the basis of the presence of some structural features, okay? And so this fingerprint is a representation, a binary representation, is a representation of the molecular structure through a binary vector, actually, okay? So 0 or 1. Well, so this is the situation we got, okay? So if you remember, we have our mass spectra, okay, which are organized in a data set with around 6,500 columns, okay, with the abundances of the spectrum. And then we have as Y matrix the fingerprints, okay, which have a length of 166 bits, okay, binary bits. And we want to make a model, okay, between our MS data and the fingerprints. This is the our aim, our goal. So of course we have we had to divide, okay, our data set in some subsets to have a training, a validation, and a test set, okay? So as usual, we use the training set to calibrate our models, our neural networks. We use the validation set for the neural networks tuning, okay? When you develop a neural network, you have to select a lot of hyperparameters, and usually you do that optimizing the performances on a validation set in order to avoid overfitting. And then we have a test set, which was used actually for the real validation of our models, okay? And we divided randomly our spectra, okay, in the 3 sets with these proportions, but we kept all the spectra associated with the same molecule in the same set, okay? So we do not have mass spectra associated with the same chemical in different sets, okay? This was done in order to avoid to get over-optimistic results in terms of validation capability, okay? So this was the situation. And then we needed some chemometric models to have to get a relationship between the mass spectra and the fingerprints, okay, in order to predict, okay, a new fingerprint given a new mass spectra, okay? So this was the final aim. So in order to do that, okay, but I will do that later, okay, just one step before. Another thing was that, as I said you before, these data were very, very sparse, okay? So when we look at the mass spectra in the training set, around 97% of the entries, okay, of the training data, the training data set were equal to 0, okay? Because, I mean, you have few peaks, okay, for each chemical. So in order to avoid, to reduce sparseness and the dimensionality, okay, we also tried to get a PCA model. So we calculated a PCA model on the training data, and then we projected in the PCA the validation and the test set. And we retained the first 500 components, okay, which explained around 84% of variance. And we tried to then calculate our neural networks starting both from the raw MS data and from the scores of the PCA, okay, to see if reducing the data dimensionality could help the modeling part, okay? Okay, so then we had to choose, okay, a way to get this relationship. So we had to choose an approach to make this relationship, okay, to be able to predict fingerprints starting from mass spectra. Here you have 2 options, okay? So usually people do 2 different things. You have to classify here, okay? Because each bit of the fingerprint is a classification task, okay? So you have to predict 0 or 1 for each bit, okay? So usually people do classification. So you have supervised classification approaches, okay? And each bit is a classification task, okay? So what you can do is to train a number of models, okay? So a number of classifiers, which is equal to the number of bits, okay? In this case, 166. Or you can use a different approach, which are the multitask approaches. So an approach which is able with a single model to predict all the classification tasks. And we preferred to use this one by means of artificial neural networks because it was easier to handle. Okay, instead of having 166 models, we have just one model. We could predict all the bits. Okay, in this case, in your artificial, I'm not going to talk about artificial neural network, but in artificial neural network, you can include in the output layer a number of nodes which is equal to the number of tasks. So you predict 0 or 1, okay, and you actually predict a new fingerprint starting from the mass spectra. Okay. Okay, so we decided to go for artificial neural network, and then we have to decide how to because this was something really new for us. Okay, so we had also to decide how to judge our model. Okay, so which kind of figures of merit you need to evaluate this kind of model where you have a lot of where you predict a fingerprint. Okay. Okay, so let's see this exemplification. Here you have a mass spectra. Let's say this is our neural network, which is trained. Okay, and so by means of our neural network, then we predict a fingerprint, so a binary vector. Okay. And then we can do it for the second spectra, and we get another fingerprint. And we can do for the third spectra, and we get another fingerprint, and so on. Okay. Then what we do, we compare the predicted fingerprints with the true one, the experimental one. Okay. And we expect these to be very similar. Okay. And you can evaluate this similarity in two ways, column-wise or row-wise. Column-wise, what does it mean? You look one column at a time, one bit at a time, okay? And you get the, let's say, usual, if you have done classification, then you can get the, you should know what is true positive, true negative, sensitivity and specificity, okay? And so one way is to get for each column, for each bit, let's say confusion matrix with true positive, true negative, false positive, and false negative. You can get sensitivity and specificity, and you can average this and have the so-called balanced accuracy, okay, for each bit. And then you can average the balanced accuracy of all the bits, okay, of all the classification tasks. So you can look at your output column-wise, or you can look at row-wise, okay? Each row is here is the predicted fingerprint, and here in the green matrix is the true fingerprint, okay? So we expect this row to be very similar to this one. And how you can evaluate similarities between binary vectors? There are many, many indices, but the most common one is the Jakarta-Tanimoto similarity. Okay, so actually what you do, you count how many bits. This A is the number of bits where you have in both vectors 1. Okay, so it's the number of common activated bits. Okay, B and C is the number of bits where you have 1 in one case and 0 in the other vector. Okay, so if two vectors are exactly the same, then the Jakarta-Tanimoto similarity is equal to 1. Okay, and so we use both these two measures to evaluate our models. Again, we had to optimize, to tune the architecture of our neural network. Here, I mean, I will be very fast, even because I didn't do that. It was a former PhD student, and she used this approach, tree-structured Parson estimator, which is a kind of optimization approach. And we use it as an objective function, okay, in order to get the best combination of all the hyperparameters for the neural network. We used an objective function to be maximized, which was based on this, the Jakarta-Tanimoto, okay, this one, the Jakarta-Tanimoto similarity between predicted and true fingerprints, experimental fingerprints, okay, on the validation set, okay. And also we try to avoid overfitting by including also this term, okay. Then again, I mean, neural networks have a random initialization. So we repeated each network 5 times, and then we actually averaged the output of the network, okay, by means of a majority voting approach. But okay, these are probably some details, okay, in order to avoid the effect of the initial initialization of the weights of the neural network. Okay, and these are the results we got, okay, in terms of balanced accuracy and Jakarta-Tanimoto similarity between the predicted and the true fingerprints, okay. On the train, validation, and test set, with the models, let's say, with the neural networks calibrated on the, let's say, raw MS spectra and on the 500 PCA scores, okay? And both approaches gave very similar results in terms of balanced accuracy and also in terms of Jakarta-Tanimoto similarity. If you look at the balanced accuracy, these models are not perfect, but they look, let's say, with an average quality. But we didn't know how to interpret the Jakarta-Tanimoto similarity because it wasn't so high, okay? So I don't know, it was one of the first time I was using neural networks, so I tried to compare these outputs with a random classifier to understand. And here you have, in these two histograms, you have the distribution of the Jakarta-Tanimoto similarity between predicted and experimental fingerprints, okay, for the test set, okay, and as usual, you have good solutions, okay, so the similarity is approaching to 1, bad solutions, okay, but at least these results are significantly different from the result we got from a random classifier. So I think we were modeling something more than noise, okay, because for sure these data are very, very noisy. But there was something in the models, okay. After that, we tried to understand, okay, with a little bit of diagnostic, which were the type of errors in our model in order to try to improve these performances, okay. Here you have many ways to do diagnostic, but we try to do it in this way. We got the predicted fingerprints, and we calculated a multidimensional scaling, okay, for the predicted fingerprints of the test set. Multidimensional scaling is something very, very similar. If you are not familiar, it's something very similar to PCA, but it's used starting from a distance matrix. Here, the predicted fingerprints are binary data, so we prefer to use this kind of approach instead of PCA, but the information is the same. So each point in this plot, which is the score plot of the multidimensional scaling, each point is one of the fingerprint predicted by our neural network for the test set, okay? Close point are fingerprints which are similar, and the color here indicates how much that fingerprint is similar to the experimental fingerprint, okay? So the darker the color, the higher the similarity between the fingerprint, the predicted fingerprint, and the true one, the experimental one, okay? So in few words, we want to get black points, okay? And if you look at this plot, actually, there is a kind of pattern, okay? Because all the good predictions are in this area, while here you have not accurate predictions, okay? And we try to look better at these results, okay? with some exemplificative situations. So for example, here you have a lot of blue points, okay? These represent the spectra, the fingerprints predicted from the spectra of the same chemical, which were very accurate, okay? So this means that for the same chemical, we had, if you remember, we could have different mass spectra. We got predictions of fingerprints, which are very similar between them, which makes sense because they are associated with the same chemical, and they are actually very close, okay? And are in this area where we have high accuracy of prediction. The orange points indicate the opposite situation. So here we have a chemical with the 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 15, 14, 15 spectra, okay, associated with the same chemical. And the prediction here were very bad because can you see that depending on the spectra, the fingerprints are very different, okay? And so, and as a consequence, all these are very different. The predicted fingerprints are very different with respect to the true one, okay, the experimental one. So we tried to look, okay, in this area, okay, this is the same plot. We tried to see which kind of chemicals we had here on the left part and here on the right part of this score plot, okay? And basically the information was that here on the right you have simple, you have fingerprints associated with simple molecular structure. On the left, you have more complex molecular structures. So our, let's say, idea was that when you have a more simple structure, probably the fingerprint is more sparse, okay? You have less activated bits with 1 equal to 1 in the fingerprint. And in that case, the neural network fails to learn from the data because you have very few activated bits. While on the opposite, when the structures are more complex, the fingerprints have more activated bits, and the neural networks probably can learn better from the data. Okay, and as a consequence, can predict better than the fingerprints. This was the conclusion we got. So, I mean, just to simplify, this model can better predict structures which are more complex with respect to simple structure, okay? Can better predict the fingerprints of structures which are more complex. Then we had to evaluate the last step of our modeling approach, okay? Because if you remember, you get a mass spectra, and then you predict the fingerprint with a model, in this case with neural networks, but then you want to compare, okay? Let's say you want to make a matching of this fingerprint with a fingerprint library, okay? And so we try to do this. How? We got, again, the 5,000, more or less 5,000 fingerprints predicted from our neural networks, okay? And for each of them, we compared the predicted fingerprint to a part of the PubChem database, okay? So we took a part of the PubChem database, including 14 million of compounds. We didn't use the whole PubChem database, just to simplify a bit the computational approach, okay? So we wanted to have an initial insight of the accuracy of prediction, okay? And on the ability of matching the correct chemical when we compare the predicted fingerprint with respect to a huge database, okay? So for each predicted fingerprint, okay, we calculated the similarity of the predicted fingerprint with respect to the PubChem, this, let's say, subset of the PubChem database, okay? And then we sorted all the compounds, starting from the compounds with higher similarity with respect to the predicted fingerprint. And then we look at the first ranking of the, at the first rankings. And of course, what we do expect is to find the true chemical, okay, in these first rankings, okay? This is actually the final aim of the approach, okay? You get a predicted fingerprint, then you go to a huge database, you look for the more similar fingerprints, and you expect that in this set of very, very similar compounds, there is the compounds which is associated to the mass spectra, which has been predicted, okay? Sorry, the mass spectra, which has been used for the fingerprint prediction, okay? These are the results we got, which are not perfect, but at least they gave us some indication. So in fact, in the 5% is in the 5% of the cases, okay, we found the correct annotation, so the chemical in the first ranking of the list. In 12% of the cases in the top 3 positions of the list. In the around 25% of the cases in the top 10 position of the list. And in the 55% of the cases in the top 20 position of the list, okay? It's not perfect, it can be for sure improved. I mean, if you look at the second reference I suggested you, okay, before, they got very better results, but they trained their model on a much significantly higher and bigger data set, okay? So they included a lot of mass spectra in their data set, okay? As I said, I mean, there are a lot of, as I would say, degrees of freedom, okay, that can be changed to increase these results, okay? For example, you can change, we used a type of fingerprints, okay, and we selected that type in order to simplify the computational step, but you could use different fingerprints with a higher length. Of course, what happens is that you will have higher dimensions and higher sparseness in the fingerprints data set. Or, for example, you could increase the mass spectral resolution. Okay, we stop it at the first decimal point. Maybe that could help, but again, you could, in this case, you will get higher dimensions and again, more sparse data set. Of course, I mean, we used only the MONA database, but because it was open, but of course, increasing the training database should enhance the accuracy of the prediction in the fingerprints. Or, of course, we use a neural network, but I mean, you could also modify the learning in the type of models to be used for the prediction. Okay, so there are a lot of things that can be changed, let's say. Okay. This is just a short list of the software we used. Okay, so for the fingerprints calculation, for the calculation and the tuning of the neural network, and for the diagnostic. And well, Rasmus, I will take just 50 seconds to say to people who is connected that we are also organizing a conference in June in Italy, in Padova, which is a chemometric conference. So, I mean, in a few days, we will open the abstract submission. So if you are interested, you can check the link to see, I mean, the topics which are covered, but it's, I mean, classical, let's say, classical chemometrics. And that's all. I would also like to let's say, thank all the members of the research group, because they helped a lot for doing this. And here you have my email. So if you have any issue or I mean, if next month you will have a question about this, I mean, you can of course write me. And this is our website where you can find the data set we produced with this study. And we also distribute all other data sets related to chemometrics and some, let's say, toolboxes and MATLAB toolboxes and stuff like that. So if you want to, of course, feel free to have a look. And that's all, Rasmus. So thanks for the attention.
Thank you so much. Very interesting. And there's already some questions. Actually, maybe you should open the chat.
Okay.
There's the first one from Stanstrup, who has a question about whether this seems to be similar to what they're doing in Sirius CSI Think ID.
Okay, so all structures predicted badly to the right contain N and sometimes other heteroatoms. So while the others are mainly polyphenols, it can be. So I mean, here this is just okay. Could be. Yeah, it could be. I mean, this is just a small set which I sampled, okay, from the two areas, okay. So I should extend, okay, then in order to confirm this, I should extend this type of analysis to the rest of the area, okay. Inside here there are 5,000 points. So but yeah, it could be. Okay, then this sounds similar to me to what they are doing in Sirius. Yes. No, they are similar. Of course, the difference is that okay, here, this is what I said, I guess, at the beginning. I found this last summer, because this is very recent, when we were finalizing our study. But yes, they use well, a different type of modeling approach, because they use kernel SVM and deep neural network. And then, as I said before, they use a bigger data set for training the networks, okay, and I mean the models, because they use merged different databases, the mass bank, the GNPS, and the NIST 2020 database, okay, and so a much bigger data set. And also they use different notation for fingerprints. So instead of using only one type of fingerprints, they used different types of fingerprints: CDK, PubChem, Clecota-Rot, McKeys, which were the fingerprints we used, then extended connectivity fingerprints. And they, how do you say, combined all these fingerprints. So they predicted actually around 8,900 bits, okay? Then, if I remember, they removed the bits where they had just 0 values, but they predicted a lot of binary bits, around 5,000, if I'm not wrong, okay? And they use, and this is part of the Sirius software, yeah.
Yes, there's more questions, so maybe you can just read them up.
Yeah, perhaps I missed the reason why we choose neural network. What about other machine learning algorithms? It's just, I mean, you can do both things, okay? We choose neural networks because it was more easy to handle just one model and predict all the bits, okay? Even because we expected that the information we had in the Y matrix, if it was modeled at the same time, it could improve the performances of the model. I don't know if this is true or not. but it was just a reason of simplicity, okay? But of course, you can use different things, and people, for example, in this work, they used neural networks, but they calibrated one neural network for each bit, okay? So different, I mean, the same method, but a different approach, in the sense that they did not use multitask neural networks, but they get a neural network for each bit, okay? But of course, I mean, you can use also other approaches if you use a single task approach, as the one I'm more used to use, I don't know, super vector machine or whatever, then you have to train a lot of models. Data pre-processing is often bottleneck with LCMS. What is your opinion? Please give some ND pointer to process them smoothly and efficiently. I mean, we started from the, yeah, you are right, but our starting data were just the mass spectra, and we just used the mass spectra. We range scaled between 0 and 1 the mass spectra, okay, but maintaining the proportion between the peaks in each spectra, because in this way the mass spectra were comparable to the weights of the neural network. But I mean, we didn't start from the chromatogram, okay, so we just got the mass spectra as starting data for our modeling. Okay, then do you think you could get better prediction for simpler molecules if you reward the ANN for predicting zeros correctly? What other molecular representation would you recommend to try? A molecule is a graph. Could it make sense to train a sequence predictor like an LSTM network used in machines translation to avoid the problem with fingerprints not representing enough of a molecule? I mean, the use of fingerprint is nice, because then it's easy to retrieve the molecule in the database. So, I mean, then you have this, I mean, PubChem or whatever, and usually the fingerprint is a standard way to represent in a holistic mode the molecular structure. And then it's more or less easy, okay, to compare the fingerprints which has been predicted to the data, to online databases, okay, and it's easy to calculate. So it's fast to calculate fingerprints. So this is why, I mean, the standard is in all these studies, the standard is to use fingerprints, okay. I don't know with a graph what would happen, but of course it could be a trial. And what kind of MSMS data are we using? Raw data or processed data, like with noise removed? And we know we use the, I mean, the data because I mean there was a lot of information available, spectra. So what we did was this kind of data curation, no more, okay. So we got the raw spectra from the MONA database, and then we tried to a little bit to cure the mass spectra. But I mean, looking at the studies around, I think this is the usually people do not also do curation. They do the whole database, and they put it in the, you know, neural network or whatever. Maybe I missed the explanation, but how was the result using the PCA scores from the MS spectra? They were very similar in terms of quality, okay. So we got very similar results in terms of balanced accuracy, and Jakarta-Nimoto similarity. Okay, so at least in our case, the use of the scores could provide a nice an alternative at least. Have you explored the Francesco del Carratore? So have you explored the possibility of training two different neural networks? One for complex structure and one for simple structure? No, I would like to do that. Yeah, there are, as I said, there are a lot of possibilities. But of course, once we have identified, some issues in the predictions, of course, then you can try to for example, to do something like this and to make like a, yeah, it's a good option to make a kind of, how do you say, a tree of models, okay? So to do a multi-block model, kind of, yeah. Then Ruda Ben Moazzini, sorry for my pronunciation, since the result of the processed data is similar to the raw data, the preprocessing might need to improve by using wavelet transformer for the time reduction and region of interest for the mass reduction. Yeah, I don't, it could be. I'm missing a bit the point here. But as I said, we did not pre-process the mass spectra. We just make some queuing, okay, and then we inputted the mass spectra in the as we used the raw mass spectra as the input in the neural networks. Okay. Okay. I don't know how much time we have, Rasmus. So I go on.
Well, I have to be at work in 12 hours, but
12 hours, okay. All structures predicted badly. No, okay, this is just okay. I already answered this. Are there any are there any web servers we can use to do this kind of prediction so that it may help with the structural elucidation process? Yeah, if you, there are online tools which are available. One is this Sirius software, okay, but there are which is actually very complex approach, which includes also this kind of machine learning and chemometric models, okay, but there are also others based on other computational approaches. So if you get the PDF, and if you are interested, if you look at these references and you look at this reference, this review, then you can find tools to be used. Okay, but I try to use it. It's not so simple. Okay, they are quite complex. And then the last question: spectra were obtained with a different energy. Would it not improve the predictions, help explain the discrepancies? Would it not improve?
maybe looking at them separately or something.
Yeah, but then you have a lot of data sets, and then you have a lot of data sets. You're right, but then you have a lot of data sets and which are which have very reduced size as a predictor. So to have the collision energy as a predictor, yeah, but I think it's if you had just one feature. Here we are using 6,500 features, and if you just add one. I think we try it, but it does not give you too much information. It does not improve the results. Maybe you could split the data on the basis of the collision energy, but then you have very I mean, you have reduced the data sets. Okay. Yeah.
I like the idea though. Maybe you should use it as a dummy variable instead of just having the voltage, and then block scale it.
Yeah, also, yeah.
Interesting. Well, thank you so much, and thank you everyone for having so many questions. If you have more questions, you can contact Davide. You can also contact me if you want, and I will direct you. So just let us know if you have an interest in discussing this more.